Welcome to The Explainer. Have you ever come across a brilliant scientific idea, one that just makes total sense, but then it seems to completely fall apart the moment it gets tested? Well, today we're digging into a fascinating paper from the Journal of Management that explores exactly why that happens, and it's all about the clues science often misses. So let's get right into it. You've got this compelling theory. Everyone's on board. But when the researchers actually run the numbers, they find, well, nothing, no effect. So is the theory just wrong? Or is something else going on? Maybe something hidden just beneath the surface? We're going to treat this like a real detective story, an investigation into the hidden truths that science can so easily overlook. All right, so our investigation starts with the very first piece of the puzzle, these hidden influences. Now, in the research world, they have a fancy name for them, moderator variables, but you can just think of them as secret ingredients. You know, the kind that can completely change how a recipe turns out. These are the clues we're hunting for. So, what exactly is a moderating effect? Well, it's when the connection between two things, say X and Y, totally changes because of a third thing, Z. And that Z, that's our hidden influence. It might not cause the outcome itself, but it can completely change the game, making the effect of X on Y way stronger, weaker, or sometimes even flipping it on its head. And believe me, these hidden influences are absolutely everywhere in the real world. For instance, researchers found that when one company buys another, their success isn't so simple. The outcome is moderated by how much financial trouble the company being bought was in. Or think about this. How your boss rates your work isn't just about your performance. It's moderated by the quality of your relationship. These aren't just tiny details. They're the critical clues that tell the real story. Okay, so if these hidden influences are the clues, how do our detectives, the researchers, go about finding them? I mean, they don't just guess, right? No, they need a special tool, kind of like a high-powered magnifying glass that's built for digging through data. And that tool has a name, moderated multiple regression, or MMR for short. For decades, this has been the absolute gold standard. It's been used in thousands upon thousands of studies to hunt for those sneaky moderating effects and see if some hidden variable is really pulling the strings. So, how does this magnifying glass actually work? It's really a three-step process. First, the researcher just looks at the simple, basic relationship between a predictor, X, and an outcome, Y. Then they add their suspected hidden clue, Z, into the mix. But the final step, that's the magic. They test something called an interaction term, which is literally X multiplied by Z. If that term lights up and is statistically significant, bam, that's the smoking gun. It proves the effect of X on Y really does change depending on Z. And make no mistake, this isn't just some boring statistical thing. As this quote puts it so powerfully, finding these hidden influences, it's at the very heart of the scientific enterprise. It's about getting past simple yes or no answers to understand the messy, complicated, and beautiful reality of how the world actually works. So, we've got our detectives, we've got their trusty tool, MMR. Looks like we're all set to solve the case, right? Well, this is where our story takes a really sharp turn. Because what happens when the detective's number one tool, their magnifying glass, is actually flawed? Yeah, it turns out that MMR, as important as it is, often has a massive critical flaw. It's a flaw that can make a researcher miss a clue that's staring them right in the face and lead them to declare a case cold way too early. And that flaw is a lack of something called statistical power. Just think of power as the sensitivity of your magnifying glass. A high-power lens, it'll spot the tiniest fingerprint. But a low-power one, you could miss a giant footprint. In research, power is simply the probability of finding an effect that is genuinely there. And the accepted standard for good power is about 80%, giving you a solid 4 out of 5 chance of finding a real clue. Now, the impact of this is just staggering. The paper we're looking at ran simulations to see what happens to power in the messy real world. Under perfect, ideal lab conditions, the power was a solid 81%. Great. But when they introduced just one common real-world problem, a slightly biased sample, the power just plummeted to 51%. Let that sink in. The researchers' chance of finding a real clue dropped from a reliable 4 out of 5 to a literal coin flip, a 50-50 shot. Can you imagine a detective having only a 50% chance of seeing evidence that's right there on the table? That's the crisis of low power. It means countless good theories are probably being thrown out just because of bad statistical luck. So what in the world is causing this massive power drain? If this is a detective story, then these are our main suspects. The factors that are smudging the lens of the magnifying glass and letting all this crucial evidence slip through the cracks. It's time to unmask them. Okay, our first culprit is the biased sample. The technical term for this is range restriction, and it is an incredibly common problem, especially when you're doing research out in the real world. So here's how it works. Let's say you want to see if a hiring test predicts job performance. But you only have performance data for the people you actually hired, the ones who did well on the test in the first place. You've restricted the range of your sample. Its crime is that it squeezes all the natural variety out of your data, and that variety is exactly what statistics needs to see relationships. And the evidence? It's damning. Like we just saw, just studying the top 80% of applicants dropped the detection rate from 81% all the way down to a 51% coin toss. All right, let's bring in our second suspect, the unreliable witness. In research, this is called measurement error, and it's basically like trying to solve a crime when all your witnesses give you fuzzy, vague, and contradictory stories. This happens when researchers use imperfect tools, like a survey question that's just poorly worded or confusing. All of that creates statistical noise that can easily drown out the real signal you're trying to find. And the paper shows just how bad it is. Even with measures that are considered good by research standards, the power to find a large, obvious effect collapsed from over 85% down to less than 45%. That's just terrible. Now, these two main culprits, they don't work alone. They have accomplices. You've got scale coarseness. That's when a study uses a clunky 1 to 5 scale when it really needs more precision. Then there's artificial dichotomization. This is a really bad one. It's when researchers take a rich variable like age and just chop it into young and old, throwing away tons of useful information. All these things quietly sabotage an investigation's chance of finding the truth. Okay, I know the situation might sound pretty bleak. The detective's magnifying glass is smudged, it's biased, it's unreliable, but don't worry, the case is not cold. The paper also gives us a really clear toolkit for how researchers can fight back, clean their equipment, and sharpen that lens. For every single culprit we've identified, there is a solution. To fight the biased sample, researchers can design their studies from the start to capture a much wider range of people. To deal with the unreliable witness, they have to use the most precise and well-tested tools they can find. And the other problems have fixes too. Use better scales, stop chopping up your data, and try to get more balanced groups. And while some of these problems can be patched up after the fact, the paper's main message is crystal clear. The best strategy is prevention. A really carefully planned investigation, designed from day one to have as much statistical power as possible, that's how you solve the case. So let's bring our investigation to a close. We've seen how these really promising theories often depend on finding hidden influences, or moderators. We've looked at the main tool researchers use, MMRD, and we've unmasked the culprits that drain its power, often leaving a detective with just a coin flip's chance of finding a real clue. This all leads us to the single most important takeaway from this whole story. When you see a study that reports no effect or no relationship, it's so easy to just assume the theory was wrong. But now we know better. A null finding isn't always a dead end. It might just be a sign that the magnifying glass was smudged. The clue could still be there, just waiting for a detective with a better tool. So I'll just leave you with this question. The next time you see a study that dismisses a really interesting idea because they found no effect, are you just going to accept it? Or are you going to ask that critical question? Was the theory really wrong? Or was the lens just not powerful enough to see the truth? Thanks for joining us on The Explainer.